Hi. In this third presentation in the playlist, we will look at general 8-bit register structures. After watching this presentation, I hope that you will be able to write VHDL descriptions for these n-bit register structures, and also to create so-called user-defined data types, which we will come across quite often in our course. So we will start by looking at the VHDL code for an 8-bit register, which is shown in this slide. In this case, what we are looking at is just a description of a collection of 8 D-type flip-flops that are controlled by the same reset and clock signals. You may still remember the VHDL description that was presented earlier for the D-type flip-flop, or take a look at it if you don't. But in this case, at the 8-bit register, and since we do not have an enable input in this case, the description is restricted to the register section or register segment, which not surprisingly is quite similar to the corresponding D-type flip-flop segment. Actually, the only difference between the two descriptions for the single D-type flip-flop and for the 8-bit register is the statement used to reset the outputs, which in this case acts upon the 8 flip-flops at once. You should keep this statement in mind because we will use it frequently when building register transfer level descriptions. Let's move on now to a more elaborate block, which is the register file. This type of block contains one input port, which is the write data bus, and one output port called the read data bus. And as indicated here, we have two address buses, and the address buses are used to select which of the various registers we want to access. One of the address buses is used to identify in which position or in which register we want to write, and this is the write address bus. And the other address bus is the read address bus, which is used to select which register should send its content to the read data output bus. And of course, we need a write enable signal which will define at which moment the content of the write data bus should be transferred into the selected register by the write address bus. Since there is no read enable signal, what this means is that the read data bus will always contain the content of the register that is addressed by the current value in the read address bus. Now, there are two things that are particularly worth of mention in this description. The first one is the generic declaration inside the entity description, which facilitates the modification of the code when we want to design register files with a different number of registers or with a different number of bits per register. In this case, B is being used to define the number of bits per register, and W is used to calculate the number of registers in this register file. This is a convenient way to specify blocks that can be customized in subsequent designs, so you should look at the generic declaration with some attention. The second thing that you should notice is the data type that is used to describe the register file structure. This data type does not exist by default in the packages declared above. So we need to create what is called a user-defined data type. You will need to do this every now and then, and namely to describe the states in finite state machines, as we will see in a later presentation. This user-defined data type is declared at the beginning of the architecture body, and the type statement here is used to build a two-dimensional array, which is in fact an array of arrays, in the form of an array of standard logic vector data types. We can now declare an array register signal, which is of the register file type that we have just defined, and use it later in our architecture description, as we will see now. You can pause the video at this point. Perhaps it will be useful to do so, to have a more detailed look at the sequence of the HDL statements in the architecture body, or the register file structure. But before you do so, there are two things that I would like particularly to call your attention to. The first one is the initialization statement for the register file, which is activated whenever the reset input is at logic level 1. We are recursively using the same statement that was used before for the single 8-bit register structure, as you may remember from the previous slide. Whenever this statement is executed, all bits in all registers will be set to 0. The second thing that you should pay attention to is that the array index that is being used to identify which register we want to access must be of the integer data type. And our address buses, as you may recall in our previous slides, the address buses were defined as standard logic vector data types. So we need to do a type conversion. But what happens is that if you take a look at the operators and type conversions table that was presented in an earlier presentation, you will see that there is no direct conversion from standard logic vector into integer. And that is why we have to perform a double type conversion first from standard logic vector into unsigned, and then from unsigned into integer. And then we can use this value as the index to access the register array. And likewise, we have to do the same when reading. Before closing, I would like to leave you one question. How would you modify this description if you wanted to have 2 output ports instead of just 1? What would you need to do to the VHDL description shown in these 2 last slides? Thanks for your attention.